All right, so the next part of the section is going to cover the idea of related rates. And related rates are, again, it's just implicit differentiation, but now we're going to have not variables of x and y. And that may make it sound like easier than it actually is. So pay attention, watch closely, but keep in mind it is just the concept of related rates, or just the concept of implicit differentiation. Okay, so a pebble is thrown into a pond. The radius is growing at a rate of 3 inches per second. All right, so here what we're talking is radius growing at 3 inches per second. And they're telling us when the radius is 2 feet. When the radius is 2 feet. Find the instantaneous change. All right, so here's that buzzword, instantaneous change. What does that mean to us? When we hear instantaneous, that means derivative, right? Find the instantaneous change of the area with respect to time. Okay, so what does that mean as a derivative? Well, if we want change in area with respect to time, then what that's saying is we want the derivative of area with respect to the variable of time. Okay, great, that's what we're looking for. So we need this. So how are we going to do this? To be able to do this, we need a function that talks about area, right? Right. To be able to get to dA dt, we need a function of area. So every related rates problem always starts the same way, for me at least, is I ask myself, what formula do I need? What equation do I need to get to? And since it's asking me for change in area, I need the area equation. Okay, great. So what we're talking about, what is the area, what's the shape we're dealing with here? Well, when we throw a pebble into a pond, doesn't it make like a ripple as it goes out, and that makes it makes the shape of a circle, right? And that is supported by the idea that they're talking about the radius. So therefore, what we need is the area of a circle. All right, well, hopefully that one you got in our back pocket. Area equals pi r squared. Okay, fantastic. Now the problem here is I need it with respect to time, and this does not have time in it. But let's go ahead and do our derivative anyway. Let's go ahead and say, all right, what I want is dt. I want to take the derivative of the area with respect to time. And whatever I do to one side, I have to do to the other side. And let's take a quick second and think about what this is saying. When you throw the pebble in the pond, as time goes on, the ripple goes out. So area is definitely a function of time, because as time changes, so does the area of the circle. Now, is radius a function of time? Does the radius of the circle change? Well, absolutely. So therefore, what we're going to say is we're doing implicit differentiation of a, and a is some function with time in it. We just don't know what it is. So we're going to do implicit differentiation. The derivative of a with respect to t, well, the derivative of a is 1, right? And then the derivative of the variable would be dA dt, which is equal to, now very similar over here, the implicit differentiation says, okay, my variable is r, that is a variable with respect to time, it is changing over time. So how do I do the derivative of a variable squared? I bring that out to the front, leave the junk alone, then times, what's the derivative of r? Well, that would be dr dt. Okay, so now, there we go. We did our derivative. We've got what we want. And I really don't need that 1, right? We've got what we want. We know the derivative of area with respect to time is equal to this function. So now, for us to be able to find the change of the area with respect to time, what do we need to be able to fill in to find out this information? Well, at this point in time, we need a radius, and then we need a dr dt. What does that mean? We need we need a number that describes how the radius is changing in time. Let's go see if we can find that information. Okay, so let's go back to the original problem. Let's go see what we can find. Let's see, I need a radius. The radius is growing at a rate. All right, so that's not the radius, that's a rate of 3 inches per second. Hey. That is this right here, isn't it? It's how is the radius changing in time? Perfect. Okay, so then the other thing I need is r. Okay, how do I find r? I just need a radius. When the radius, oh, there we go. When the radius is 2 feet. So I have all the information I need. I've got everything right here. So I know dA dt is equal to 2 times pi. Now, what is the radius of our circle? 2 feet times, and how is it changing? 3, we got something I don't like here. Let me fix this real fast. This is 2 feet times 3 inches per second. I don't like that our units aren't the same, because if I multiply these numbers, 3 times 2 is going to be weird. It'd be 3 inch or 6 inch feet. I don't know what that is. So let's get these to be the same units. Let's get them to match up. It's easier, in my opinion, to get the feet to turn into inches, because we all should know, hopefully, that there are 12 inches in a foot. So therefore, I can therefore go ahead and say, all right, dA dt is equal to 2 pi. And so since there's 12 inches in a foot, 12 times 2 is 24 inches times 3 inches, and then per 1, so I don't need to really write that. So other than, I guess, for the units, so we'll keep it there. So therefore now what we're going to see is dA dt is equal to, let's see, 3 times 2 is 12, or sorry, 3 times 2 is 6, 6 times 24 is, well, 6 times 4 is 24, and then 6 times 2 is 12, so it's 144 inches, pi, times pi, inches squared per second. Now, if you wanted to, you can multiply by 3.14 for the pi, but what I really wanted to focus in is, does the unit seem to make sense? How do we measure area? Area is measured in inches squared, feet squared, so that's fitting. And then our denominator, time, seconds. So it says our area of our circle is growing at 144 times pi inches squared per second when the radius is 2 feet and it is growing at 3 inches per second. All right, so the idea here, let's look back at related rates and see the big idea. So when we do a related rates problem, typically the variable we're going to be doing the derivative with respect to is time. That's why they talk about it as a rate, because the rate at which something changes, we usually talk about it, it's a change in distance over change in time, or the change, it'd be the change of something over time usually. Now when we say they're related, what we're saying is, when we write our whole equation, the area and the radius both changed with respect to time. When we did our derivative, we don't do it with respect to r or with respect to a. They have a relationship. They both are change as time changes. So that's why we call it related rates. So then when we do our derivatives, it's again just implicit, and the idea is the derivative of any variable is going to be the derivative of that thing divided by the derivative, the change of that thing divided by the change of time, so dA dt. So when I do the derivative of r, it's dr dt, and then all of our other derivative rules hold just like normal. All right, so for this next one, I tried to pick something that, again, geometry, but something that was not circles, because sometimes that freaks people out. So take a quick read, pause the video, take a read, make sense of it. Okay, so here we go. We're going to deal with a ladder sliding down a wall where the distance between the bottom of the wall and the base of the ladder is increasing at 3 feet per hour. The ladder is currently 12 feet away from the wall and 16 feet above the ground. Fantastic. How quickly is the top of the ladder falling? Now, most of you probably can conceptualize this idea, but it makes it so much easier if you draw a picture. At least I think it is. So what I'm going to do is say, all right, here's my wall, and I have a ladder leaning up against the wall. I'll make the ladder black. Ladder leaning up against the wall. Now we've got the ground coming out here, and you will notice that makes a triangle. So hopefully what jumps into your head, like the last problem, it was circles, and we jumped to a circle formula. Here, I think we're going to need to use some triangle formulas. Okay, now let's keep filling things in though. And the rule of thumb is, you'll notice that they make a mention of a lot of different things. The ladder is currently 12 feet away from the wall and 16 feet above the ground. How I like to think about this is if that number is changing, if as the ladder slides, if those numbers are changing, it needs a variable. So This ladder is sliding down the wall, so it's coming down this way, and the base of the ladder is going out that way. So the distance that the base of the ladder is from the corner of the wall is changing, so it's going to need a variable. Let's call it, I don't know, b for base. Okay, then the height that the ladder is above the ground is changing as well, so let's call that h. All right, so now let's see what else is going on here. Now they do tell us that the distance between the bottom of the wall and the base of the ladder is increasing at 3 feet per hour. So we're going to need that later. And if you hear, is that a rate of change, or is that just a value, the distance? Well, it's a rate of change because they're talking about it's 3 feet per hour. It's a distance over time. It's a slope. So they're giving us a slope. They're giving us a derivative there. They're also telling us the ladder is currently 12 feet away from the wall. Okay, so that's a distance because there's no change, there's no per, it's just a unit of measurement. And they're also telling us that it is 16 feet above the ground. And once again, that's changing. That isn't going to be a constant 16 feet, but that 16 feet is, again, it's just a unit of measurement. It's a height. So I think we've got everything highlighted we need to be able to plug in later. But so the first thing we need to do, because I think we captured all the information we need to on the picture, we'll find out. The first thing we have to do is come up with an equation, something that relates the height and the base, because that's what they gave us, and to answer the question. The question is saying is how quickly is the top of the ladder falling? So what they're saying here is like, how fast is it going down? Well, again, speed would be how is it going down? Well, that's a measurement of height, so change in height over change in time. So again, what we just said is I need some equation that has h in it and b in it. Well, let's just start thinking about formulas that we know about triangles. Give it a pause, take a thought. Okay, I'm going to go ahead and say one that we always like to jump to is Pythagorean Theorem. A squared plus b squared equals c squared, right? So we haven't labeled the side, but maybe I'll call it c for that, or you could call it L for the length of the ladder, whatever you want to think of it. I'll leave it as L. So therefore, a squared plus b squared equals c squared, or h squared plus b squared. It doesn't matter. All right. Now, can I do this derivative? Do I know how to do this derivative? Well, let's find out. What is the derivative of h? Now, and I guess I should say, what variable are we going to do the derivative with respect to? And for me, I would say we want to do it with respect to time, because if you remember the question was asking for the change in height per time. How quickly is the top of the ladder falling? So the change in the height over time. All right, so the derivative of h, how do we do the derivative of h? Well, that would be bring the exponent out to the front, so that's 2, leave the junk alone, times the derivative of the junk, so dh dt. Hey, good news, that's what we said we needed. This is what we need, perfect. All right, plus, how do I do the derivative of b squared? Well, bring the 2 out to the front, leave the b alone, or leave the junk alone, times the derivative of the b, so that'd be db dt. Okay, so we'll have to figure out what that is. And then that's equal to, now how do I do the derivative of this? Well, bring the 2 out to the front, leave the junk alone, dl dt. All right, now here comes the moment of truth. We know we're trying to solve for this, so that's a good sign. We've got something we need. Now we need to be able to fill in the rest of the numbers. At this moment in time that they're asking the question, do we know the height of the ladder? Well, that was what I highlighted here in pink. They told us the height is equal to 16 feet above the ground at this instant. So we can go ahead and fill that in. Okay, so that's 2 times 16. There we go. Now, dh dt is what we're solving for, so we don't know that. Plus 2 times b. What is b? B represents the distance from the wall to the base of the ladder. Okay, and I think they told us that, right? The distance between... Oh, there we go. The ladder is currently 12 feet away from the wall. All right, so there's a 12 right there. And then we need the next part of that equation, which was db dt. What does that mean? The change in the distance in the base in time. Do we know how quickly the base was sliding away? And I think we did. It's right here what I did in yellow. The distance between the bottom of the wall and the base of the ladder is increasing at 3 feet per hour. All right, so therefore, that would be 3. And if you wanted to, you could be putting units on all this stuff just to make sure your units are all matching up. But the idea here is you'll notice everything's measured in feet and hours, so that makes it easy. Okay, so we got that part. So now that's equal to 2 times the length of the ladder. We didn't know that. And in the problem, they never told us that. Shucks. Okay, well there's one little wrinkle, but you'll see it's not a big deal. Because then the next thing, what does dl dt mean? Well, dl is the change in the length of the ladder divided by, or not divided by, the change in the length of the ladder per change in time. Well, how is the length of the ladder changing as it slides down the wall? Is the ladder breaking apart into pieces? Is the ladder collapsing? Or is it just sliding? Well, it's just sliding. They don't tell us anything. So that means, how is the ladder changing? Well, it's not. The change in it is 0. So therefore, this whole term right here is multiplied by 0, so it's just 0. That's why that actually works out okay. All right, so we know it's equal to 0. Now, you can see, we can now answer this question. Because we've got dh dt, that's what we need, and everything else is now a number. So we can just do a little bit of algebra and solve for dh dt. And so let's see, 2 times 16 is, 12, 32. dh dt, and then over here 2 times 3 is 6, 6 times 12, 672. Subtract that over to the other side. So now dh dt is equal to negative 72 divided by 32, and then we're able to go ahead and simplify that down to dh dt. Whoops, excuse me, my button's pushing. There we go. 9/4, negative 9/4, I believe. So what does that mean? Does it make sense that we have a negative? Well, let's see. What we're talking about here is the change in height over change in time. And if you wanted to, by the way, you could also write this as a decimal, which would be negative 2.25, which might be a little more natural to talk about it. So I'll use this decimal version of it. Okay. So what is this saying? The height, when it's a negative, it means it's getting smaller. Does that make sense? Well, yeah, the ladder's falling down. So the ladder is going down at 2.25 feet per 1 hour. So it's falling at a rate of 2.25 feet per hour at that moment, because it's an instantaneous rate of change. Now that speed may not be constant the entire time, but just at this individual moment that we're talking about, we know dh dt is the change in height with respect to time is decreasing at a rate of 2.25 feet per hour. Okay. Now, is the area under the ladder increasing or decreasing at this moment? That's another interesting idea. Well, if we want area, if you want, you can go ahead and pause this video and give it a shot. But the question is asking us here, is the area under the ladder increasing or decreasing at this moment? So what they're asking us is how dA dt, how is the area changing, right? So what do we need? To be able to do that, we need the area formula. And the area of a triangle is 1/2 base times height. So the derivative of this then would be dA with respect to time, because it's asking how is it changing at this moment in time. So dA dt. Now here's the fun part. We have to remember these are two variables that are multiplying. So therefore we have to use product rule. All right, so I'm going to split this up into two separate functions. There's one function. There's the other function multiplying. So the first one would be 1/2. The derivative of b would be 1, and then dB dt. Let me scoot that over a tiny bit. dB dt. There we go. And then so we did the derivative of the first function, leave the second function alone. Then plus, now leave the first function alone, I should say, or first factor, however you want to look at it. Do the derivative of the second. What's the derivative of h? 1 dH dt. All right, so now, is the area under the ladder increasing or decreasing? Well, how is the area changing at this point in time? Well, let's see what we can fill in. So at this point, we've got dA dt is equal to 1/2. Do I know dB dt? Well, yes, that was from the last problem, right? In the previous part, they told me it's increasing at 3 feet per hour, so that'd be a 3. Then we knew the height of the ladder. It was, I believe, 16 feet off the wall, plus 1/2. Now, did we know the base? Do we know how far it was away from the wall? Yes, we did. That was 12, okay? So 12. And then do we know dH dt? Hey, that's what we found in the last problem. We found it's negative 2.25. All right, perfect. So to be able to answer this question now, we just got to pop this in the calculator and see what we get. Or do a little bit of head math, whatever you prefer. And let's see what we get. Okay, so this is what I got when I substitute those numbers and just kind of ground it out, and I got 10.5. So stop and ask yourself, what does that mean? What is the meaning of that? Well, if you put that over 1, it helps us read it against this notation. And it says our area is, well, if it's a positive number, that means our area is getting bigger. If it was a negative number, then it would mean our area is getting smaller. So the change in area is 10.5 feet squared, because it's area, per 1 hour. So to answer the question, is our area getting bigger or smaller? And this tells us it is getting bigger at this moment. Will it always be getting bigger? Well, of course not, because if you think about the triangle, right, as this ladder slides down, even though the base will be moving further and further and further away, you can imagine essentially at some point in time, the ladder will be laying completely on the ground. Well, not how I just drew it, but you get the idea. The ladder will be laying completely on the ground right on top, and the area would now be 0. So it will not always be getting bigger, just for a while. So nonetheless, this was just a couple problems to get you going into related rates. And the idea, again, just to recap, the big idea was, first thing we need to do is come up with an equation that has the variables we need to talk about in it. And usually the problem gives you a big hint. They'll start talking about area, they'll start talking about sides of a length of a triangle or something, and there's your tip off. You say, okay, I need equations of triangles, or I need equations of circles. They're talking about radius and blah, blah, blah. So you come up with an equation, you take the derivative, and you don't really worry about too much. You don't really worry about saying, oh my gosh, I have B's and L's and whatever. Who cares? You just say, what is my derivative? And then say, do I have all the information I need? If you do, great. If you don't, then you might have to start going back and looking at, is there a better formula, another formula I could have picked? Or is there a way that a relationship I know where I can substitute in for one of my variables? But aside from that, the related rates portion is relatively simple. It's just the implicit differentiation. The hard part's the word problem, and that's why these are everybody's favorite. Okay, best of luck.